Today we start one important topics, okay, related to Gram-Schmidt orthogonalization process. Now we start from one theorem. Okay, we write it here. One theorem. Let W be a subspace. Okay, W be a subspace which is finite dimensional, which is finite dimensional. Okay, which is finite dimensional of an inner product space V, of an inner product space V. Understood? And let Y belongs to V. Okay, then there exist unique vectors U belongs to W. Then there exist unique vectors. There exist unique vectors U belongs to W. Okay, and Z belongs to W5. Okay, such that Y equal to U plus Z. Understood? Furthermore, okay, if here V1, V2, Vk, here V1, V2, Vk is an orthonormal basis for W, is an orthonormal basis for W. Okay, then what happened? Then U equal to, here I equal to 1 to K. Okay, Y Vi, here Vi. Okay, understood? We write it proof now. We write here proof of that theorem. So what this theorem says, this is one finite dimensional subspace. We know about that one subspace with finite dimensional. That means what? That means number of, that means vectors in basis is obviously less than plus infinity. Okay, and obviously one inner product space V, well known about that inner product that satisfies some conditions about some, that means we define some inner product and obviously some conditions satisfied by those inner products with these elements of V. Then we talk about this V, the space V, and with inner product we call it inner product space. And then we're also going to further Y belongs to V. Then there exist unique vectors U belongs to W, Z belongs to W path, such that Y equal to U plus Z. Furthermore, if V1, V2, Vk is an orthonormal basis for W, orthonormal basis means we know about that, or they are orthogonal, and obviously basis means linearly independent and generates W, and then obviously they are orthonormal means orthogonal with norm of VI equal to 1, then this one is orthonormal basis. So what happened? Well, so what we have to prove, there exists an unique U and Z. U belongs to W, Z belongs to W prop, Y equal to this one. We write it in this way. This Y is an arbitrary element of V, and obviously further we use this one. If V1, V2, Vk is an orthonormal basis for W, then U equal to what? U equal to, also write it linear combinations of this VI's. Okay, understood? Not a problem at all. This one is too easy, I think. Now we're going to proof of that. Okay, now start this proof now. Let V1, V2, Vk, okay, be an orthonormal basis for W. be an orthonormal basis for W. We know about that. Orthonormal basis for W means what? Okay, not doing this one more. Let be what? U belongs to W. Okay, then what happened? Let U belongs to W. Then what happened? And Z equal to Y minus U. Okay, understood? Then then we also shows that, okay, clearly U belongs to W and Y equals to this one. Y equal to what? Z plus U. Okay, Y equal to what? Z plus U. Understood? Now we show that what? We write it now. We show that here Z belongs to W path. Okay, Z belongs to W path. This means what? This means we also known about that every factor of W obviously perpendicular to Z. That means this one is too easy. The inner product of every factor of W with Z becomes 0. I understand that. I think this one is too easy. Now I write it now. Okay, it suffices to show that. It suffices to show that. It suffices to show that what? Z orthogonal to is Vj. Okay, Z is orthogonal to is Vj. Understood? Not a problem at all. Now also going to discussion further. Where is that portion and going to further discussion of that. Okay. Then what we have to prove? We have to prove that this one is too easy. One factor from this W. We take Vj from W for any J. We write it here for any J. Okay. Then in a product of Z Vj, we show that this one equal to 0. Okay. How we do it? Okay. This one equal to what? Z equal to, we know about that Y difference U, and here Vj. Are you understand? This one is too easy. Now we do it in this way. This one equal to what? Here Y difference U equal to what? U equal to, we write it in this way. I equal to 1 to K. Okay. Here Y Vi. Here Vi. Okay. And here Vj. Any problem? I think not a problem at all. Okay. Then what happened? Then we talk about that this one is Y Vj difference. Here I equal to 1 to K. Here Y Vi and here Vi Vj. Understood or not? I think all are understood that. Okay. Then this one is what? This one equal to Y Vj difference I equal to 1 to K. We put it here. Then what happened? Then this one is Y Vj. Okay. Otherwise Vi Vj equal to 0. Understood? If I not equal to J. Then what happened? Then obviously we're getting this position 0. Then our that means our requirement is done. Okay. What we prove now? We prove now Z inner product of Vj equal to 0 for any J. Okay. And Vj belongs to W. Understood? So what happened is here, this implies that Z belongs to W path. Not a problem at all. We do it too easily. Okay. Now we're going to discussion of uniqueness. Okay. So we erase that portion and going to further discussion of that. What happened is here. Okay, to show uniqueness of U and J, to show uniqueness of U and Z. Okay, so what we do? We suppose that what? y equal to u plus z, and we also set another one u dash plus z dash. Okay, what happened? We know about that u belongs to w and z belongs to w power. In this way, u dash belongs to w and z dash belongs to w power. Okay, any problem? I think not a problem at all. Okay, then what we do it here, we write it in this way. Then u difference u dash equal to what? Z dash difference z equal to what? Equal to, we write it in this way, w intersection w far, and w intersection w far equal to what? 0. I've known about that because if w be a subspace and w far be a subspace, then obviously common intersection is 0, otherwise no one is belonging to this vector. Okay, or sorry, belonging to this two space. Okay, no vector is belonging to this two space. So here what? Then u equal to u dash, this gives, this implies that, and z dash equal to z. So not a problem at all. What we prove here, y equal to u plus z be unique. Okay, u belongs to this w and z belongs to this w path. So this problem is done. That means we prove this theorem easily. Now we're going to discuss some corollary of that. Okay, so we erase that portion, and how this one y and u happen, we also see it in a figure. Okay, then we also see start from this one, and obviously perpendicular this, then here 0, and here this one is u, this one is y, then this one is y difference u equal to z. Understood? In this way we also develop this one. So now we erase that portion and going to discuss another corollary.